Right. Welcome to our lecture 12. Today we're going to finish talking about Cauchy sequences where we left last time, and we're going to start talking about subsequences. Cauchy sequences are in section 10 of the textbook. Subsequences are in section 11. So that's what we are going to do. Last time we defined a Cauchy sequence here. A Cauchy sequence is a sequence where all of the elements are very close to each other when their index is large. So when m and n are bigger than n, this implies there's an inequality here, which means that your elements are close to each other for this indices. Our goal was to show that Cauchy sequences converge. And the reason for this is that this gives us a criteria to show that a sequence is a convergent sequence without saying anything about the limit. We just say this. This has nothing to do with the limit, but if we know this, then we know that it has to be a convergent sequence, and that's why we are interested in this concept. This is the end of our section 10. In section 10, we were giving several different examples of how to show that some sequences are convergent. The first of these examples was monotone sequences, and then we gave a theorem saying that if the lim-inf and lim-sup coincide, then the sequence is convergent. And now we are going to combine this to say we're going to use this result about lim-sup and lim-inf to show that Cauchy sequences are convergent sequences. So that's our first theorem today. Theorem 10.11 of the textbook. A sequence is a convergent sequence if and only if it is a Cauchy sequence. This if and only if means two things. It means convergent implies Cauchy, and Cauchy implies convergent. So in other words, convergent sequences and Cauchy sequences are exactly the same thing. They are equivalent concepts, different ways of expressing the same idea. Now, to recall, we first gave several lemmas. We already showed one direction of this. This is lemma 10.9. We showed that convergent sequences are also Cauchy. That's one direction. And we also showed that Cauchy sequences are bounded sequences. So now, to prove this if and only if, we already did one direction. We already showed that convergent implies Cauchy. And now we need to show that Cauchy implies convergent. From lemma 10.9, we showed that convergent implies Cauchy. So it is left to prove that Cauchy implies convergent. So to show this, we have to show that this implies this. So let's start assuming this. So let Sn be a Cauchy sequence. We have to show that it converges. To show that it converges, we can apply our previous theorem by theorem 10.7. We only need to show that the lim-inf of Sn equals the lim-sup of Sn. And this is the reason why we introduced this concept, because now showing this allows us to conclude that the sequence is convergent, which is what we want. So now we reduced our goal, which is to show that this converges, into showing that A equals B. And let's go back to our strategy from next time to give ourselves an epsilon of room, a little bit of room. If you want to show that A equals B, we have to show two things. That A is less than or equal to B plus epsilon, and that B minus epsilon is less than or equal to A. And these two things combined for any epsilon. If we can show these two things combined, then this implies that A equals B. That's the general strategy, and that's exactly that type of statement that we're trying to prove, so we're going to apply this strategy. And in this case, the first part is easy, it's for free, because we already know that the lim-inf is always less than or equal to the lim-sup. No epsilons required here. This is always true. Ints are less than sups, and lim-infs are less than lim-sups. So we must show the other direction. This is our goal. So this is our B, this is our A. We must show that B minus epsilon is less than A, or that B is less than A plus epsilon. We must show that lim-sup of Sn is less than or equal to lim-inf of Sn plus epsilon. So this is our goal now. And I want you to see how we are transforming a more complicated proof like this theorem. A sequence is convergent sequence if and only if it is a Cauchy sequence. We are reducing it to simpler statements here that A is equal to B. And this equality we are reducing to this inequality here. Now, this is all that we want to prove. So we are reducing to something simpler and simpler. And inequalities are easier from an analysis point of view. Analysis, we can think of the theory of inequalities, triangle inequality, and applications. And always an inequality is easier to show than an equality, especially if we have a little bit of epsilon to breathe, a little bit of room. Okay, so this is our goal. That's the strategy. Now let's go to the formal proof. So let epsilon be greater than 0. We are assuming that our sequence is Cauchy. Then there is an integer n such that Sn minus, first, such that m and n bigger than big N implies Sn minus Sn less than epsilon. This is the definition of Cauchy. Let me go back to the strategy for a moment. We want to show that the lim-sup is equal to the lim-inf, or that the lim-sup is not much larger than the lim-inf. This makes sense from this assumption. We are assuming that the sequence is Cauchy. What it means to be Cauchy is that your big elements are very close to each other. If all of your big elements are close to each other, then the smallest elements, the smallest large elements, have to be very close to the largest large elements. This is why this makes sense, and why this makes sense. So that's what we're trying to formalize. So the elements are close to each other, and equivalently, we always like to write this absolute value inequalities in terms of two inequalities. Sm minus epsilon is less than Sm is less than Sm plus epsilon. Now, in this case, we are trying to show, we're trying to show an upper bound for the lim sup. So we're talking about lim sups are upper bounds, we're talking about upper bounds here. So here we are only going to care about this part. So let me write it again. Sn less than Sn plus epsilon. But this is true for all m and m larger than n. This means that Sn plus epsilon is an upper bound for all of these elements. Upper bound for the set of Fn with n larger than big N. And then this means that this is also an upper bound for the sup, because the sup is the least upper bound. So the sup of Fn with n larger than big N is less than or equal to Fn plus epsilon. Since this is the least upper bound, the least upper bound has to be smaller than any upper bound. Let's call this quantity here, it's an upper bound, so let's call this Un. And now let's put this epsilon to the other side. So we have Un less than or equal to Sm plus epsilon for all m larger than n. And equivalently, Un minus epsilon less than or equal to Sm. So we did one thing, we have two variables, n and m. Here, we left the m fixed and we considered the set of the n's. Now let's do the opposite. Let's leave this fixed and consider the set of the n's. Because this inequality is true for any m bigger than big N. And this means that Un minus epsilon is a lower bound for the set of Fm m bigger than big N. This means that this is also a lower bound for the inf, because the inf is the greatest lower bound. Un minus epsilon is less than or equal to the inf. Since this is the biggest lower bound for this set. And we can call this quantity Ln, L for lower bound. So combining, what we get is that Un, let's put this epsilon to the other side, Un is less than or equal to Ln plus epsilon. And this means we know that this sequence is decreasing, this sequence is increasing, so that the lim sup, by definition, the lim sup is the limit of the UNs. It's less than or equal to Un, which is less than or equal to Ln plus epsilon, which is less than or equal to lim inf of Sn plus epsilon. This is an increasing sequence, so this is always less than the limit. Or we can also see this as taking the limit when n goes to infinity in this inequality. This goes to lim sup, and this goes to lim inf. And combining, we get lim sup of Sn less than or equal to lim inf of Sn plus epsilon. And that's exactly what we wanted to show. And we wanted to show this we showed this for any epsilon greater than 0, since this is true for any epsilon. Then this means that lim sup is less than or equal to lim inf. And we also know that lim inf is always less than or equal to lim sup. And combining, since we have the two inequalities, the lim inf is equal to the lim sup. And this implies that Sn converges by last theorem, which is what we want to show. And that's it. Now, some comments about this proof. Clearly, this is false if we are talking about the rational numbers. Consider, for example, we know that, say, the square root of 2 is like, let me check with my calculator quickly, 1.4142 something. 41, 42, 1, 3, 5, and so on. So consider the sequence of rational numbers given by approximating its digits. So A1 equals 1, A2 equals 1.4, A3 equals 1.41, 1.414, or 142, and so on. So here, let's say AN is the decimal approximation of square root of 2 with n decimal digits. So one digit, including the integers, 2, 3, 4, so on. And in particular, AN is a rational number. For example, this is 14 over 10, this is 141 over 100, and so on. This is a sequence of rational numbers. This is a Cauchy sequence. Why is this a Cauchy sequence? We know that in R, since this is the sequence of decimal approximations, it's possible to show that AN converges to the square root of 2 as a sequence of real numbers. And by the theorem that we just showed, this means that AN is a Cauchy sequence. We can see this because, for example, A4 is very close to A5 because the difference is only in the fourth decimal digit. So, for example, A4 minus A5 is 0.0002, and so on. If you go larger and larger, the difference between terms is going to be smaller and smaller. So it's a Cauchy sequence even in the rational numbers because it's a sequence of rational numbers. But in the rational numbers, if we are thinking only in the rational numbers, AN, the limit does not exist. It's not a rational number. Limit of AN does not belong to the rational numbers. We know that the square root of 2 is rational. So this shows that in Q, Cauchy sequences not always converge. They don't always converge to a rational number. Which makes sense because we know that they actually converge to a real number. That's the point of the real numbers, that we are filling in the gaps. And this is what the theorem is telling us. This theorem tells us that there are no gaps. If you have a sequence where the terms are getting closer and closer to each other, there cannot be a gap, so the sequence has to converge to a real number. This is telling us that, in a way, this is another way of saying that there are no gaps in R. So this is an important theorem for this reason. And why is this true for the real numbers and not for the rational numbers? What's the difference between Q and R? Because the axioms defining the sets were almost all the same. There's just one different axiom, and that's that the real numbers have the completeness axiom. This is the only difference between the real numbers and the rational numbers. This tells us that bounded sets have a supremum and an infimum. So it tells us that the supremum exists and the infimum exists. And since this is the only difference between the real numbers and the rational numbers, that means that we are necessarily having to implicitly use this in this proof. So the completeness axiom is inside of this proof, implicitly. Let's write this here. Completeness axiom. Completeness axiom inside. In this here. And where are we using the completeness axiom? We have to be using it somewhere. We are using it whenever we talk about liminf and insup, we are talking about infs and sups. By definition, this is the limit of an inf, this is the limit of a sup. So for that to even exist, for these objects to exist, we are applying the completeness axiom here. To justify this step, to say that this exists. And it's in this step where we are using this special axiom that allows us to say that the real numbers are complete. There are several different ways of saying that the real numbers are complete. This theorem is also another way of saying it. We can say that the real numbers are complete because all Cauchy sequences converge. Or we can say that they are complete because they satisfy this completeness axiom. And at some point we have to use it, and it's at this point where we are using it. So that's an important thing to keep in mind. So let's go. With this, we are finished with section 10. The goal here was to give criteria to show that sequences converges, and this theorem is the combination of all of that. Convergent sequences are exactly Cauchy sequences. Now we're going to talk about subsequences, new topic. We are in section 11 of the textbook now. Sorry, what is a subsequence? Let's say that we have a sequence. This is just the general idea. We have a sequence A1, A2, A3, A4. A subsequence is that you just take some of the elements, you choose some of them, but all the way up to infinity, you always have more and more elements. And that's it. For example, the subsequence of even of even indices. This would be A2, A4, A6, A8, and so on. So the idea is to choose infinitely many elements of the sequence, and this is what we call a subsequence. We are taking here all of the even indices, so these are infinitely many, that's why we call this a subsequence. And here I just chose them more or less randomly without any rule at all. That's also perfectly allowed. You don't need a rule, just you choose whatever, and you can call this a subsequence as long as you somehow choose infinitely many elements. We can also choose everything except the first one. This is also a valid subsequence or whatever. Now here's the formal definition. The formal definition can look a little bit messy, but it's really just one way of formalizing this idea. Definition 11.1. So let Sn be a sequence so a subsequence of this sequence is another sequence let's call this other sequence T sub k. But we have to say that all of the elements of the sequence are part of the original sequence somehow. So now one way of saying this is where so each of the indices k is one of the indices here. So for each k, there is a positive integer nk such that it has to be an increasing sequence. So n1 less than n2 less than so on, less than nk less than nk plus 1, all the way up to infinity. And tk is s and k. So the n something is a sequence of natural numbers. This is a natural number. For this natural number, we have this element of the sequence s. So in this way, the tk is just a selection of some or even possibly all of the SNs, taken in order. So what this means here is that we are taking the elements in order, skipping some of them, but taking them in order. So if this was our original sequence, we can take the subsequence here. So this would be the first one, this would be the second, third, and fourth. So that's why we mean in order that we are maintaining this same order here. So in this case, this would be my T1, T2, T3, T4. Here for the subsequence of even indices, this would be my T1, T2, T3, T4, T5, and so on. So let's consider this example here, and let's see how this fits inside of this definition. Let's consider an arbitrary sequence. So the subsequence of even indices is A2, A4, A6, A8, and so on. So in this case, we have T1 equals A2, T2 equals A4, and in general, Tk equals A2k. In this case, this 2k here is exactly the nk here. So Tk is Snk, so Nk is 2k. So here, N sub k equals to 2k, which is an increasing sequence, like we say here. So let's see. Let's see a more concrete example. This is actually example 1 in the textbook. Let Sn be the sequence defined by Fn equals n squared times minus 1 to the n. So we can take the subsequence of positive terms So first, let's write down this subsequence. So the entire sequence. So the sequence is n. With the sequence, we start negative, minus 1, 4, minus 9, 16, minus 25, 36, minus 49, 64, minus 81, and so on. We have always perfect squares, and we're alternating the signs between minus and plus. So we can take that subsequence of positive terms. And that's the sequence, not this one, not this one, this one, not this one, not this one, like this. So it's 4, 16, 36, 64, and so on. And to be more precise, this is the sequence S sub n k for k in n, where n sub k equals 2k, because we are taking only the even indices, the entry 2, 4, 6, 8, and so on. So this is the sequence. It's 2, 4, 6, 8. And that is how we write it more formally according to the definition. Let's see another example. This is also in the textbook. It's a bit more complicated than just even and odd, so it's useful to see it. Let's consider a sequence in terms of a sine of pi n over 3. Consider the subsequence of positive or non-negative terms So first, let's consider the entire sequence. So we have sine of pi over 3 is square root of 3 over 2. Sine of 2 pi over 3 equals 1 half. 2 pi over 3. Sine of 3 pi over 3 is just sine of pi. This is 0. And then the sign looks something like this. pi is here, 2 pi is here. So after pi, everything repeats but negative. So sine. So now the entire sequence is going to be something like this. Square root of 3 over 2, 1/2, 0, minus the square root of 3 over 2, minus 1/2, 0, and now positive again, and so on. So here we have some positive terms, then negative, then positive, always with a 0 at the end of each section, and it goes something like this. So the sequence of the negative terms S and K is going to be, we take only this, we skip this, but we have the 0, and then we take this. So square root of 3 over 2, let me move everything a little bit. 1/2, 0, not this one, not this one, but we have this one. So we have another 0, because 0 is not negative. Now we have this, 1/2, 0, and then the same thing will happen, we have another 0, and so on. So it repeats in groups of 4 in this case. So in this case, we are taking, here are the indices. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. We are taking the indices 1, 2, 3, not this one, not this one, then 6, 7, 8, 9. So the indices we have. And 1 equals to 1, and 2 equals to 2, and 3 equals to 3, and 4. We are not taking the 4, we are not taking the 5, so the next one is 6. And 4 equal to 6, and 5 equal to 7, and 6 equal to 8, 7 equal to 9, and so on. We don't particularly need to have any formula for the NK. It doesn't need to have a formula, it's just something. These are just the indices that we're choosing. We are choosing this one, this one, this one, not this one, then this one, this one, this one, this one, and so on. And these are the choices, that they are always increasing. This is our subsequence, and that's it. At the end, this is just a way of formalizing the idea of that we can somehow choose some of the elements of your sequence and call it another sequence. So the next theorem is important. It's one of the very important theorems about subsequences that we are going to use all of the time. So it's important to understand the proof. Let Sn be a sequence. This theorem tells us about when there exist certain subsequences converging to something. So sequences and okay, converging to something. And not only are we going to get subsequences converging to something, it's going to tell us about monotone subsequences. That is either increasing or decreasing. So this has three parts. So first, let t be a real number. Then there is a subsequence of Sn converging to T if and only if the set integers where their sequence is very close to T very close to T is infinite for all epsilons. So we have two conditions. Condition one, there's a subsequence converging to T. Condition two, this set is infinite for any epsilon. This is telling us that there are infinitely many elements very close to T, as close as you want. And this one is telling us that there is a subsequence converging to T. Subsequence converging to T means that you can choose infinitely many elements that are going to be very close to T. So this is why we are saying the same thing. We are saying a subsequence is choosing infinitely many elements, so we can choose infinitely many elements very close to T if and only if there are infinitely many elements very close to T. We are saying the same thing in two different languages, a language of sets and a language of subsequences. Let me write this down. We are saying the same thing in two languages. So this theorem is basically a theorem about translating things into the language of subsequences, which is a particularly useful language. Language of subsequences. And language of sets. In both cases, we are saying, what we're saying here is that there are infinitely many terms close to T. This is not saying that the entire sequence converges to T, because to say that the entire sequence converges, we are saying that all of your large terms are close to T. Here we are not saying that all of them are close to T. We are saying that there are infinitely many of them, maybe not all of them, but infinitely many that are close to T. So it's a little bit different. That's why we're talking about subsequences that converge instead of just saying that the entire sequence converges. This is an if and only if. We are proving two things, that 1 implies 2 and that 2 implies 1. Let's write down the other statements. This one is for a real number. There are analogous statements for plus and minus infinity. Again, we're able to say the same thing in two languages, the language of subsequences and another language. So in the language of subsequences, Sn has a subsequence with limits plus infinity if and only if. Now I'm going to translate to the second language. Sn is unbounded above. But this means that you can choose elements that go to plus infinity if and only if your sequence does not have any upper bound. And the same but for minus infinity. If, and only if Sn is unbounded below. And furthermore, in each case, in all of the 3 points, the subsequence can be taken to be monotone. So for today, we are going to show the implications in this direction. We are going to show that if there is a subsequence, then something happens. If there is a subsequence, something happens. If there is a subsequence, something happens. For an if and only if, we have to show two things. We're going to do one of them here for now. So for part one, assume that there is a subsequence converging to T. S sub nk converges to T. Then this means that we have to say that this means that there are infinitely many elements in this set. Of course, if we look here at the picture, this is our T. That means that we can take any epsilon. And if this sequence converges to T, this means that they're going to be, all of your large elements are going to be here inside. For large K. Here, the index is K. So we are taking the limit as K goes to infinity. So now it's not N, it's K. K is the one that's large. And then K is the one that's large. If there are elements here, if all of your elements are here, this means that the number of elements inside here is infinite, and that's exactly what we are saying here. That the number of elements in this set, that's exactly this set, is infinite. So for example, we have to show that this set is infinite for all epsilon greater than 0, so let epsilon greater than 0. And consider the set. Consider the set A to be the set of integers, positive integers, such that Sn minus t is less than epsilon. No, maybe let's copy this. Since there's a subsequence that converges to t, by definition, for this epsilon, there is an integer n such that k larger than n implies s and k minus t less than epsilon, but this is just telling us that s and k, that the nk belongs to this set A. Belonging to the set A just means that you are a natural number such that this Sn is very close to t, and that's exactly what we're saying here. This is true for all k, and since nk is increasing, since nk less than k plus 1, less than k plus 2, and so on, and all of those belong to A for all k larger than n, this means there are infinitely many elements in A, so A is infinite. This means that A is an infinite set. This is exactly what we were trying to prove. All right. Let's see, for example, the second one. We are assuming that you have a subsequence that goes to here, that goes to plus infinity. This means we have to show that your sequence is unbounded. Let's go into the details. We have to show that the set of all elements is unbounded above. This means that this does not have any upper bound. We want to show that an upper bound does not exist, so we can do it by contradiction, for example. That there is an upper bound. There is an upper bound m greater than 0. This means that as n is less than or equal to n for all n in n. But this is not possible since their subsequence goes to infinity. But since s sub nk goes to infinity, this means that for this specific m, there is a natural number n such that K larger than big N implies S and K bigger than N. This is the definition of going to infinity. But this contradicts this, because this has to be true for all N. In particular, this has to be true for Nk, and this is false. This contradicts that S sub Nk has to be less than or equal to N. This is a contradiction. And this proves the proposition, because the contradiction is that this cannot have an upper bound, so therefore this set is unbounded above. Now the third one, it's the same, but with minus infinity instead of plus infinity. I leave this to you to check the details as an exercise. So far we showed the implications that if you have a subsequence, then something happens with your sets. Now we want to show the other implications, that if something happens in the language of sets, then something happens in the language of subsequences. And we are going to leave the proof of this for next class. And yeah, even the implications that we showed so far, it's important to understand them because it allows us to get used to the language of subsequence, which will be an important language for the rest of the course. So we are missing the other implications. And we're going to stop here.